So I'm going to be talking about philosophy and models. And like last time, I'm going to start with the question of progress in philosophy and the question of what constitutes progress. And of course, progress or the lack of progress in philosophy is often compared unfavorably to progress in natural science. And many philosophers have a kind of bit of an inferiority complex about that. And the way that such comparisons typically go is that people are thinking of progress in natural science as consisting in the discovery of new universal laws, new laws of nature. And then, of course, when one looks at philosophy, it seems that philosophy very rarely discovers new universal laws. And so it seems that by that standard, it's making very little progress. And so it seems that philosophy is doing much, much worse than natural science, if one thinks of the comparison in those terms. But actually, that's, in many respects, not an appropriate standard. And it's not appropriate even when one's thinking about progress in natural science, because a lot of natural science is not, in fact, in the business of discovering new universal laws. It's doing something else. It's dealing with complex, messy systems whose behavior does not obey distinctive universal laws, so that looking for them is pretty nearly hopeless. If one really means by universal here, I mean completely unrestricted, without exceptions. Now, of course, these messy systems that are studied in many areas of science, I mean, they still obey the laws of fundamental physics, and we may assume that there are some absolutely universal laws in fundamental physics. But just giving those laws doesn't tell us what's distinctive about the behavior of the complex system at issue. Those laws are just not at the right level to give us the explanations that we're looking for. So an example of that is in biology. So biological systems, of course, they obey the laws of fundamental physics like all other physical things, but we actually want to understand them in biological terms. And progress in biology typically does not take the form of discovering new universal laws of biology. Biological systems are just too messy to satisfy many completely exceptionless but still informative universal generalizations stated in biological terms. I remember talking to a professor of biology who was also interested in philosophy, and so sometimes went to conferences on the philosophy of biology. And he said that he found quite a bit of the discussion not really relevant to the kind of research that he was doing and was mainly familiar with in biology, because they were still thinking of science as looking for universal laws, and that was just not something that he and his colleagues were doing. They were doing something else. And instead, the kind of progress in biology that someone like him was looking for, it often takes the form of building better models of biological phenomena. And such such a model it's a simplified description of a case of the phenomenon in precise mathematical terms. For example, it may be using differential equations, which is if it's a continuous model, or difference equations if it's a discrete model. And these equations, they'll typically be describing changes in the state of the system over time, how the state of the system evolves. And so in principle, when you have the behavior as modeled, described in such mathematical terms, you can then derive how it will evolve over time. You can derive various conclusions about what patterns there will be in the behavior of the system. And as I say, it's a deliberately simplified description. The classic example of a model in biology, which is often used in the literature, is the Lotka-Volterra model of the evolution of a predator population and a prey population. For example, wolves and sheep, or I think in the original case it was different species of fish in the Adriatic Sea. So the model considers only changes in the number of predators and the number of prey. So the relevant variables are just time, the size of the predator population, and the size of the prey population. And the model, it ignores changes in the environment. It ignores the age profiles of the population, which may also be changing. It ignores the role of other species and so on. And so it's not pretending to be an accurate description of what's going on, and not a fully accurate description. It's quite deliberately ignoring a lot of factors which are not totally irrelevant. It just in order to get something which is mathematically tractable. And the model did help scientists understand puzzling kinds of pattern in the sizes of two such linked populations, a different kind of oscillation that was going on in the population size of because they were involved in differential equations which they could solve, and so they could predict how the evolution would go for. Of course, there were various parameters which get fixed in the model, but for different parameters, how it would look. One striking feature of this case is that the model, in a way, is impossible. It doesn't strictly describe a case that could evolve, and there's a very simple reason for that, which is that it characterizes population growth and decline by differential equations, and so it's representing the changes in the population numbers as continuous. But of course, the size of a population is always a cardinal number, if you like, a positive, a non-negative integer. It's an answer to the question, how many? And so it must change discretely. You can't have the square root of 2 wolves or 1.76 wolves or something like that. So, as well, what it's describing is not simply something that doesn't happen. It's describing something that couldn't happen. But even so, a continuous function can still be a good approximation to a discrete function, and the continuous function may be mathematically more tractable. So there are good mathematical reasons for working with differential equations, even though they do involve this kind of impossible idealization to continuous change in what is in reality a discrete variable. And the idea is that it may still be the case that the continuous function, which is measuring the population change, is a good approximation to, as it were, some discrete function which would be possible. So one sort of way in which one model can be a better model than another of a given phenomenon is by being a closer approximation to actual cases of the phenomenon, and at the same time not much less mathematically tractable. Because if you have a model that is more realistic, but it's more realistic by being so complex that we can't actually solve the equations, we can't actually derive the relevant features of the model, then it's not really serving its purpose in science. So that's where it's an intractable model is excluded for that kind of reason. And so if we think of the case of biology in terms of such models, it can consist in replacing one model of a biological phenomenon by a better model. And what I've just said here gives some kind of at least initial sketch of what the betterness of one model as opposed to another might consist in. And I mean, I think in many cases, it's kind of easy to assume that the purpose of these models is to make some kind of quantitative prediction. I mean, in the case of the Lotka-Volterra model, it's although the particular numbers are not so interesting. What's interesting are the general patterns of the kind of how the oscillation in one species is linked to the oscillation in another in population size. But it's important, particularly once we start thinking about the comparison with philosophy, where quantitative prediction clearly does not play a major role. It's important to realize that quantitative prediction is not exactly what a lot of these biological models are concerned with. So, a standard example of that is that, supposing that we're interested in explaining why evolution normally involves two sexes rather than three. A good way to do that is by building models of three-sex evolution and to study how that would work and to find out what would go wrong with three-sex evolution. And so it's not, we're not concerned with predicting carefully measured numbers or anything like that. I mean, of course, you could say, well, we're concerned with why the number of sexes is typically 2 rather than 3, but that's only kind of rather trivially numerical in the way that quite often in philosophy we're concerned with, whether there are 2 categories of something or 3 or whatever. We're not. That isn't an example where we're interested in, as it were, an exact measurement. It's something much more qualitative, and what we're concerned with doing is understanding why things are the way they are, and why they're not some other way. And in order to explain that, what we want to do is to ask, well, what would it be like if they were that way? And and we may be able to show that a species that did operate by evolution with three sexes would get into difficulties of certain kinds, might not survive. And I mean, there's still we can still talk about one model being better than another, even in these cases where we're not concerned with quantitative prediction, because, for example, we can say that one model of three-sex evolution is better than another because it's a closer approximation to what three-sex evolution would be like if it occurred. So when we're thinking about these models, I mean, given that the models themselves involve all these simplifications and so on, that they're not aiming at direct accuracy, one can wonder, well, do they actually provide us with any knowledge, or is it some other kind of cognitive value that we're getting from them? But I think, in fact, we do get knowledge in the sense in which knowledge requires truth from these models, and we get it in at least two different forms. One is that we get precise knowledge of mathematical features of the models. We could simply know those by normal mathematical means, by deriving consequences from the defining equations of the model. But we also get a vague knowledge of the relative goodness of different models of a given phenomenon. As when we're concerned with comparing two models, we may be able to discover that one of them is a better model than another of the, let's say, the biological phenomenon that we're concerned with, because it explains more of the relevant features of the phenomenon that we're concerned with. And so when we combine this, as it were, the precise mathematical knowledge with the vague knowledge of the relation of all that mathematics to the target physical or natural phenomenon, then that gives us overall valuable knowledge of the target phenomenon. So I just for the sake of an example, I've been talking about biology, but model building is certainly not confined to biology, even though, of course, biology is concerned with very complex and messy systems. And model building, it also occurs in physics and other natural and social sciences as well, to some extent. And so even in physics, even when we get down to a fairly fundamental level, we may still be engaged in model building. And one example of that, in even as well the level of fundamental physics, is that that often what we're studying are causally closed systems. In other words, systems which can be treated as completely isolated from the rest of the universe, just systems of where all we have to take account of are the interactions of 2 or 3 particles or whatever it is. And of course, those kind of closed systems, I mean, they typically don't exist in nature, because there's always some interference from outside, some maybe very, very small gravitational interaction with external bodies. So that in a way, just dealing with closed systems by itself is a kind of model building assumption, which you get almost all the time, because if we don't make assumptions like that, the mathematics becomes so complex as to be totally intractable in many cases. So I think now thinking about what bearing that has on philosophy, the preliminary conclusion that we should draw is that if we are comparing progress in philosophy to progress in natural science, and much progress in natural science is of a model building kind, the natural question to ask is whether there is also progress in philosophy of a model building kind. And the mere fact that we're not getting much in the way of discovery of new universal laws in philosophy is not decisive. It does not show lack of progress, because we might be getting progress of this other kind. And just, when we think about things initially, it looks as though, in fact, philosophy is very well suited to a model building methodology. It seems apt for model building because it deals with the human world, and the human world is notably complex and messy. Human being, each human being is an extremely complex and somewhat messy system, and of course the human society is even more complex and even more messy. And I mean, this is already, as it were, something that you might think in a way of Kant as referring to when he made that famous remark that out of the crooked timber of humanity, no straight thing was ever made. And as it were, the straight thing would be the model, or it might be the model. And I think the role of the human in philosophy is worth thinking about. Of course, the philosophy is often classified as one of the humanities, and that suggests that all philosophy should be concerned with human things. And that isn't quite right, but an awful lot of it in practice is. So when we're talking about epistemology, we're normally concerned with the epistemology of human cognition. And although we might be interested in, for example, the knowledge of that non-human animals have, still the main example that we want the epistemology to cast light on is human cognition. And when we're doing philosophy of mind, that almost always what people are talking about most of the time is philosophy of the human mind. When we're doing philosophy of language, we're almost always talking about human language, even if occasionally we might mention other kinds of language, animal language. When we're talking about philosophy of art, we're talking about the philosophy of human art. When we're talking about about ethics, we're talking about the ethics of human action. And in metaphysics, of course, some of metaphysics is not really specifically about the human. It might be fundamental metaphysics. It's talking about the universe as a whole. Of course, that in itself is also a very complex system. But we're also dealing with human reality when we're interested, for example, in the metaphysics of personal identity, what it is for one person to continue to exist over time, and so on. I think when we reflect, we see that at least a very large proportion of philosophy has an urgent concern with the human, and therefore with the complex and the messy. So we might expect philosophy to be a model building subject. But that raises the question, how much model building has philosophy actually done? And it's certainly not been a salient philosophical method, although some of that may partly be because philosophy has rarely been thought of in terms of model building. But of course, in these areas, there is some interaction in both directions between what people are doing and what they think they're doing. So if they're not thinking in model building terms, they're also not going to give themselves the aim of building a model of something that they're interested in. And that means that they're less likely to build a model, even though it might be possible for someone to do, in effect, to build a model without really thinking of what they're doing in those terms. But I do want to argue that there has, in fact, been a fair bit of model building in philosophy, even though people haven't always been thinking of it in these terms. Even though I would say, at least, probably even now, it's been only to some extent a minority activity in philosophy. So one kind of case is model building in epistemology, and quite a lot of that happens. So there are in the tradition of Bayesian probabilistic epistemology, a lot of model building goes on, and some of it is it might not actually be described as a model, but it really is. So, for example, in a lot of epistemology, people talk about lotteries, where you have a certain number of tickets and just one of them wins, and each ticket has an equal chance of winning, and so on. And even there, there's a little bit of model building going on in such kind of very simple models of uncertainty, because, for example, it might be that, one kind of realistic point is that that in a normal lottery, you don't know how many tickets have been sold, and so you don't actually know just what the probabilities are. Whereas a typical lottery model will assume that it's known how many tickets there are in the lottery, so that as you know what all the probabilities are. And although you could have a model where there was uncertainty about the number of tickets sold, that would be a much, much more complex model. In fact, you might be going in a direction already of something that's a bit mathematically intractable. I mean, you could probably do something with it, but so that's an example of how something that may simply be described as an example, of the fair lottery, it's really a simple sort of model, and it's one that is used over and over again in epistemology, just as a kind of a simple example of uncertainty, which we then look to see what various epistemological theories have to say about it. And then there's also the tradition of epistemic logic, which I was talking about last time, founded by Jaco Hinteker and people like Van Bentham, who I know has lots of connections with China, have also contributed to a lot to that tradition. And of course, when we're talking in terms of logic, model has a slightly different and meaning in relation to the semantics of epistemic logic. But the fact is that the models of epistemic logic that are models in the logic sense, they're also models in the kind of philosophy of science sense that I'm talking about at the moment. So if we look at specifically at formal epistemology, a lot of it is actually concerned with model building activity. And formal epistemology is certainly one of the most active and growing areas of epistemology at the moment. Then, if you look at moral and political philosophy, which you might think of as an area that's much less susceptible to model building methodology, in fact, you do find it when decision theory and game theory are being used. And I think an example of that is the prisoner's dilemma, where it seems that if we have a simple model of a situation in which the result of each agent behaving rationally is that things are worse for everyone, and I think in that sort of case, the prisoner's dilemma brings out in a very clear way a certain kind of challenge to moral thinking about the relation between what's good for the individual and rational for the individual to pursue, and what's good for everyone. And by using not just prisoner's dilemma, but various other kind of variations on it, we can already set up a lot of very challenging situations for moral and political theories, and as it would test them out on these simple cases. And although the simple cases are kind of idealized in various ways that are not realistic for actual moral choices, nevertheless, it seems like a pretty good test of a moral or political theory to see whether it says something sensible about these very simple cases. And if it doesn't say something sensible about these simple cases, we shouldn't be too confident that it's going to say something sensible about the more complicated cases, which you might think of as harder ones. And this kind of methodology, it is used to a certain extent in moral and political philosophy. I mean, there's a little bit of it in, for example, in John Rawls's theory of justice. One of the most influential, well, probably the most influential work of political philosophy in the past half century. So although it's not a dominant methodology in these areas, it's certainly a recognized one, which makes a distinctive contribution. Another case which is worth thinking about is in the philosophy of language, which of course uses formal methods quite a lot, especially in formal semantics. And there are definitely things which look like models. I mean, one kind of example is Carnap's model in meaning and necessity of a very simple intentional language, where it's clear that he's not thinking of this as in itself realistically similar to a natural language, but it's he wants to show how it is possible for an intentional language using what we now call possible worlds, although Carnap talks about them as state descriptions, how it's possible to work and for the meaning of complex expressions to be a function of the meanings of their simpler constituents. And so in that case, I think Carnap is is thinking in something like model building terms. And I think maybe a much more surprising case, but one still worth thinking about in this setting, is Wittgenstein's language games, which, of course, he's not describing them in terms of differential equations or anything like that, but they do have some key features of models, in that there is a very clear, precise, explicit, and relevantly exhaustive description of the rules of the game, how it works, and so on. And he's looking at the language games just to get, as it were, a feel for how language can work, in particular in its relation to practice and the non-linguistic world. Although, of course, Wittgenstein would certainly not have liked the comparison with the methods of natural science. I mean, he was very hostile to any attempt to see philosophy as similar to a natural science. I think a related question is to what extent we can think of all the contemporary work that's been done in formal semantics as model building. And I think it's fair to say that the people doing it typically don't think of what they're doing as model building. They think of it as trying to produce completely accurate descriptions of how the meanings of terms in natural language work and interact with each other, and so that, as it were, any kind of inaccuracy shows that there's something wrong, which is not exactly the model building spirit. But it might still be that when we look at this work, that we can see that it is making some kind of progress of a kind which is more similar to that of a model building tradition than to that of a law discovering tradition. Because when these initial attempts at the initial hypotheses about the semantics of something are rejected, then when they turn out to be counterexamples to them, it's not as though that's simply a failure. It may be that we've already produced quite a good model of a phenomenon that we're interested in, even if it's not wholly accurate. And in some cases, it might be that really good models are all that we can expect. And I think that might be true even more in pragmatics, where we have to take account in principle of all the complexities of the speech situation, that maybe the kind of understanding that we're getting is something more like model building understanding than like an understanding which is aspiring to as it were, to define laws of language. Now, I think all of what I've been saying is a bit sort of abstract, and so what I want to do is to give you a feel for how model building can work in philosophy by actually developing a specific type of model for philosophical purposes. And the particular one that I'm going to give you, just because this happens to be an interest of mine, is one which I think casts some light on the origins of vagueness, of imprecision in thought and language, and in particular on the way in which there are borderline cases for many of our terms. Now, one thing that I haven't yet brought out fully is that I mentioned that model building in natural science is typically dynamic. It doesn't have to be dynamic, but typically it is concerned with the evolution of a physical system over time. Well, the kinds of example that I've been giving you of model building in philosophy, they've actually been static. So, for example, the lottery examples, or the other examples in epistemology, those are mainly static ones. I mean, I guess there's with the lottery, there's the before and the after and so on, but there isn't the. I mean, those kind of models, they don't involve the evolution over time through, as it were, many stages of a system, and that's so with many of the models that you find in philosophy, but I don't think that that's an essential difference between natural science and philosophy, and so I'm going to consider a dynamic model for philosophical purposes, just as it were, to make the comparison closer. Although, as I say, I don't think it's not that all models in philosophy by any means are dynamic ones. So I'm going to describe to you in a series of stages a kind of toy model, or it's really a whole class of models. It's a type of model, and of course that's often also what we're dealing with in science, because often the models that we have in science, they involve a number of numerical parameters. For example, with the Lotka-Volterra model, population change. I mean, there are parameters that you have to set about the various to put in the differential equations, and then they're fixed for as well a single model. But really, what's called the Lotka-Volterra model is a family of models corresponding to different parameters, and so this is going to be like that too. And so I'm imagining that we have a kind of logical space of points in a sort of metaphorical sense, which are kind of possible cases, and that there's going to be a relation of indiscriminability in some respect on them. So, for example, this logical space, it could be the space of all possible shades of color. In fact, that's the way I'm going to tend to talk about it. So you could think of this as color space on which all shades of color are mapped out according to similarity relations on various dimensions, such as brightness and hue and so on. And this relation of indiscriminability is one where you can't tell the difference. And for example, that might be where just by looking at two shades by the naked eye, you can't tell that they are actually different shades. So one logical property of indiscriminability, which this model will build in, is that it's reflexive, so that each point is indiscriminable from itself. You can't discriminate something from itself, because discriminating is recognizing a difference, and there isn't a difference in the relevant respect. And we're also going to assume that if X is indiscriminable from Y, then Y is indiscriminable from X. So the order, it doesn't matter, but, just to keep things nice and simple. And then slightly more complicated is that we're saying that this space of points is ultimately connected. So what I mean by that is that between any point in the logical space and any other point, there is a path which takes you from one to the other, which consists of a finite number of steps. And at each step, you go from a point to an indiscriminable point from it. So that as with each step, you can't see that there is any difference where you're going. But nevertheless, ultimately, all the points are connected in that way. And that's a very common feature of many kinds of space. I mean, after all, if we just think of ordinary physical space in the kind of Euclidean way that we normally think about it, that you can get from any one point in Euclidean space to any other point in a finite series of steps which are close enough together that they, if you had some faculty of limited discrimination, you couldn't tell the difference between them. And even if we go to non-Euclidean space, that doesn't have to disrupt this condition of being ultimately connected. So as it were, you can get anywhere from anywhere in enough steps, but without, you don't have to take an infinite number of steps to somehow do it. And I'm also going to assume that that there's at least one point is discriminable, so not indiscriminable from another, because if all the points in the space were indiscriminable from each other, then this would be a rather trivial example. And one consequence of that is that you sometimes get cases where X is indiscriminable from Y and Y is indiscriminable from Z, but X is not indiscriminable. In other words, it's discriminable from Z. And that kind of non-transitivity is a logical consequence of the previous conditions, because if we just take those 2 points that by non-triviality are discriminable from each other, and then by ultimate connectedness, we know that there is a series of steps taking you from one to the other, where at each stage you're going from a point to a point that's indiscriminable from it. And so if transitivity held, then it would mean that X and Y had to be indiscriminable from each other, but we've, by non-triviality, we've chosen a pair that are not. So the non-transitivity of indiscriminability is just a consequence of the other conditions that we've imposed on this space. And the idea is going to be that we want some kind of systematic procedure for classifying points of the logical space using some finite vocabulary, and probably not a very large vocabulary even, of words, C1 to Cn. And if we're thinking of this in terms of color, then these words could be just ordinary color words like red, yellow, blue, green, orange, purple. And I'm thinking of each of these color words as associated with its own point. So C1, the word C1 is associated with a point P1, the word C2 is associated with a point P2, and so on. And I'm also assuming that these points, these special points associated with the words in this way, are they're all discriminable from each other, because otherwise they wouldn't be able to serve the function that we want them to serve, which is that we're going to that we're going to use each of these points as a prototype for the associated word. So, for example, associated with the word red, there'll be a particular point on the color sphere which we're using as a prototype of red, which we might call focal red. And then that makes it obvious why we want all these prototype points to be discriminable from each other, because if we had a prototype for red that we couldn't tell apart from a prototype for yellow, then they would not be able to do their job. And we're also going to lay down a condition that we want no point to be assigned to two different color words. So, for example, we don't want any shade to count as both red and orange, or red and purple, or blue and purple, or whatever. And that seems to be the way in which our classification terms typically work, where we have this kind of classifying vocabulary, that distinct terms are supposed to be mutually exclusive, at least when we're talking about the sort of basic range of terms. So we want to make sure that the extensions of these different words don't overlap. But once we've respected those first two conditions, we also want, as far as possible, for indiscriminable points to be assigned the same color. So I'm calling this coarse-grained, because we want, as far as possible, we want to avoid any distinctions between things that are indiscriminable from each other, because such distinctions are hard to they can't be observed, and so they're hard to implement. And so we want, as far as possible, we want to avoid that. And as far as possible, we also want each point to be assigned to some color or not. So we want, and I've called this jointly quasi-exhaustive, because we may not be able to achieve this completely, but in general, this is what, as far as possible, we want that roughly speaking, that for almost every point on the color sphere, there is a color term that can be properly applied to it. And now here's where the dynamic element is going to come in, that we're going to assign points to, they're going to assign them words, like colors in the example we're thinking of, by an iterative process. So there are going to be many stages of this process. And when we're talking about the set of points assigned to a given color term Ci at a stage n in this process, it'll be a discrete process, one step after another. We're going to call that Ci of n. And that's the set of points that are classified by Ci at stage n. And at the very first stage, stage 0, the only assignments that we've got are of the original prototypes. So for each color term at stage 0, there's just one point which is assigned to it. So if it's Ci, it's Pi. So that for example, that the only point assigned to the word red would be this prototype of red, focal red. And then the action is going to come from the dynamic rule for getting from the assignment at stage n to the assignment at stage n plus 1. And the rule is going to be this, So if we want to know whether a point X is going to be assigned to a color term Ci at stage n+1, I mean, that has to be based on what the assignment was at the previous stage. And so, first of all, we want a point that's indiscriminable from X, that some such point was assigned to Ci at the previous stage. So we're going to do this by doing it locally by looking at the points indiscriminable from X. So we want at least one of them to have been assigned to X at the previous stage, because to motivate, to assign to this color term Ci, because we want there to be at least one such point to motivate the choice of Ci for X at the next stage. And then we also want that no point that's indiscriminable from X was assigned to any other color term at the previous stage. So in other words, if there are several rivals amongst this group of points indiscriminable from X, if there are different color terms competing with each other, because one of them was assigned to one of the points in this little local area around X, and another to a different one, then we're just not going to try to decide between them. We're just going to not assign anything. So that's the dynamic rule. So it's that if there's a point indiscriminable from X which was previously assigned to the color, then we'll assign X to the color as well at the next stage, as long as there's no competition coming from any other of that kind coming from any other color term at the previous stage. And so now what we want to do is to see how this kind of assignment process works in some examples. And we're just going to consider a series of points on the spectrum from yellow to red with 3 classifying words: yellow, orange, and red. Sorry, I haven't used colors for this. But, at each stage, we're going to label unassigned points just with a little dash, points assigned yellow with a Y, points assigned orange with an O, and points assigned red with an R. Successive stages are represented by descending horizontal lines. So as the iterative process proceeds dynamically, we'll get lines going down the page. And I'm going, just to keep things really simple, I'm going to assume that a point is indiscriminable just from the points which are at most one step away. So that means, in effect, that we're just looking at a one-dimensional slice to keep things simple. And there you've got, there's a yellow point on the left for the Y, an orange point in the middle with the O, and a red point on the right with the R. And for each of the points, it's just itself and its two immediate neighbors on the left and the right, which are indiscriminable from it. And so what happens at the next stage is that the classified areas with these color terms, they expand because they're not getting any competition from any other color terms because they're too far away. So the Y area has expanded because that one that's the second on the left, it was next, the previous one of the points that it's indiscriminable from, the one on the far left was yellow at the previous stage. So it's going to be yellow too, because on the other side, we're not getting any competition. And then this orange expands in the same way in the middle, and red expands in the same way on the right. And now the expansion goes even further. So we've got all but one of the points has now been classified. And notice that so far we're just getting an expansion, and we're not losing any classifications. And another feature is that the terms originally assigned each color, they continue to be assigned that color. But now, if you look on the boundary between orange and red, there's a problem, because the orange point is also next to a red point. So that if we were to, the far right orange point is next to the far left red point. And so those points are indiscriminable from points that are classified the other way. And so when we look at the next stage, those points have gone back to being unclassified, because they were involved in this, as it were, competition between orange and red, where we would amongst the things that indiscriminable from the points. So we gave up the attempt to classify there. Whereas on the left, what we've got is we've got a single point, both at the present stage and at the previous stage. So there's a present point. There's just one point between the yellow points and the orange points, which has remained unclassified, and it can't get to be classified because it's indiscriminable from both yellow and orange points, and so it doesn't meet the criterion for being orange, and it doesn't meet the criterion for being yellow. But it's still, as it were, serving a purpose, because it's keeping the yellow points apart from the orange points, so that all the yellow points are discriminable from the orange points, because they're not immediate neighbors. So there's that unclassified point in between. And if we continue this process, we start going into a cycle where we're back to line 5 is actually the same as line 3, and so if we just continue this process, it would just go on cycling, where on the boundary between yellow and orange we have something stable with as were an unclassified gap, but it can stay that way. Whereas on the boundary between orange and red, we've got this kind of instability, because we keep classifying points as orange, and then because they're now clashing with an indiscriminable point that's been classified as red, they go back to being unclassified, and that just continues indefinitely. And of course, if you think about it, you realize that this has come about because originally there were an odd number of points between yellow and orange on the first line, and an even number between orange and red. So we've got slightly different phenomena on the boundary between yellow and orange, and the boundary between orange and red. And so just even in this very simple case, we've got two kinds of borderline case. So between yellow and orange, one case is never assigned a color because it's indiscriminable from a case assigned yellow and from a case assigned orange. But between orange and red, two indiscriminable cases oscillate between assigned and unassigned, because assigning them both colors violates coarse graining. So this is, in a way, it's actually predicting the occurrence of borderline cases where we have points which cannot be stably classified by any color according to the rules that we're using. And sorry, let me just go back for a minute. And this actually corresponds to things that you can see in the literature on vagueness, because sometimes borderline cases are described in terms of, as it were, disagreement and oscillation and stability, and sometimes they're just described in terms of the being a case which can't be classified. And in fact, what this model predicts is that you can have cases of both kinds, but they're still clearly borderline cases, because they never stabilize in how they're classified. And one advantage of having done this by completely precise and explicit rules for moving from the classification at one stage to the classification at the next stage is that it enables us to prove various results about how the classification process works in the model. So, for example, one thing that you can prove quite easily is that if a point is assigned a color at 2 successive stages, it's assigned that color at all subsequent stages too. I mean, that's a feature of this fairly specific model that I'm looking at. There'd be other models with maybe a more complex structure of the indiscriminability relation where you didn't get that. But in the model I'm talking about, the type of model I'm talking about, you get that feature. So that as where the color assignment only has to survive 2 successive stages to become permanent. And you can also show that the prototype is assigned the associated color at all stages, so that once we've taken a particular point as a prototype for a given color, we never give up the classification of that particular prototype point by that color. And it's also a consequence of the rules that we've got that any 2 colors are mutually exclusive at each stage. So those are ways in which we can check that things are working the way that we would want. So that's a very simple example, but it shows how we can use a model to explore how a reasonably natural classification procedure can lead to phenomena like borderline cases in different ways, and to identify structural features of the procedure, so that, as it were, it shows how these kind of features of classifications of the occurrence of borderline cases, how natural they are, and it also identifies a way in which they can occur in different ways, but as it were, between the stable unclassified and the oscillating borderline case. So that's really a very just a toy example, but I've used that one because it's reasonably easy to explain without very much background, and so, of course, with more powerful models, we can get more insights into what sort of possibilities they show and so on. But I think that both philosophers and non-philosophers tend to underestimate how much progress of a model building kind philosophy has made. And I'm certainly not suggesting that model building is the only methodology that we should use in philosophy, but we can use it as an independent test of results that were originally reached by other methods. So an example of this is the existence of Gettier cases in epistemology. So Gettier cases are cases where you have justified true belief in the relevant sense of justified, but you don't have knowledge. And so the way that Gettier cases have normally been argued for is by the use of thought experiments. But in fact, one can show that if you have appropriate models of the justified true belief and knowledge relation, that you can, if you reflect on those models, you can pretty much predict that there will be Gettier cases, and you can predict that without doing any elaborate thought experiments. So that, as it were, really what we're getting here is independent support for the results of the thought experiments. And it's not because the thought experiments themselves are illegitimate or anything like that. It's just that from a scientific point of view, it's better to have some kind of convergence of different types of support on a given conclusion, because it makes the case for it more robust. And you could also say that the thought experiments are giving some independent support to the conclusions reached by the model building methodology. It's just in this case, it was the thought experimental methodology that came first. And so, as I've said, this does not make either method redundant. Using both, it makes a more robust methodology than using either one by itself. Although in some cases we may have to rely on a single method, in general, making our methodology more robust is a prudent thing to do. As I say, not because any of the individual methods are so bad, but just because they're not 100% reliable, and so independent support should be welcomed. I think it's worth saying that many philosophers may have difficulty in getting used to the use of models. And I think that as it were, it may be that to begin with, many, and in fact, in practice, I've seen this, that many philosophers find models a kind of somewhat counterintuitive way of thinking. They may have trouble with the role of unrealistic simplifications in models. And I think this has to do with the role that counterexamples have traditionally had in philosophy. And so I think that, as it were, a kind of traditional philosopher's reaction to a model may be, oh, I can give a counterexample to that, therefore it's wrong, and therefore it's just not, the model isn't helping us because it's inaccurate. And I think if you want to get a feel for what's wrong with that reaction, you think that it's like trying to give a counterexample to a model of the solar system by insisting that a planet is not a point mass. I mean, it's true that a planet is not a point mass, but making that objection misses the point. I mean, in fact, it's very common in models of the solar system and similar types of model to treat a planet as simply a mass concentrated at a single point of zero extension. And making that simplification makes the mathematics tractable in a way that it might well not be if you didn't make that. I think it's pretty clear that somebody who made that objection to the model of the solar system would be that they would be missing the point. And I think philosophers have got to understand that when we're dealing with a model building methodology, that we've got to think in those terms, so that counterexamples are not playing the role that they were traditionally expected to play. And it's not because counterexamples are somehow incorrect. It's just because we're not going for 100% accuracy. We're willing to sacrifice some accuracy in order to get deeper understanding. And so in the model building methodology, what displaces a model is not a counterexample, but a better model. And I mean, I've had experience of this talking to and collaborating with colleagues in economics. Theoretical economics is a much more model building discipline than philosophy, and so economists find it quite strange that that Gettier is so celebrated for these counterexamples, and I've heard economist friends of mine saying that Gettier's paper would not have been considered publishable in economics because they're going for a model building methodology where it's taken for granted from the beginning that whatever you're doing will just be a model and will have counterexamples. Of course, it's unfair to Gettier because the analyses of knowledge that he was objecting to were not proposed just as models. They were actually proposed as exceptionless generalizations. But of course, if philosophy evolves in such a way that we expect fewer exceptionless generalizations and more of what's being offered is being offered as a model and not as it were a law of philosophy, then we've got to get used to this kind of methodology where counterexamples are not the main thing, and what displaces a model is not a counterexample but a better model. So if you don't like a model, your job is not to think of a counterexample to it, but to think of a better model. And in some ways, that can give work in within this sort of methodological paradigm a more constructive quality than the just the method of counterexamples tends to have. I mean, in many cases, I mean, I don't want to exaggerate the difference. The better model may have actually been inspired by the attempted counterexample and may even explain it, so that if you notice some, as it were, feature of the phenomenon that the model is inaccurate about, if you can produce a better model that does have that feature, then that may well displace the original model. Although the better model, it will also have to have the kind of good mathematical features of the original model, or at least a lot of them, in order to be a real competitor with it. So far, I've been talking about the simplifications that we build into models as if they're mainly motivated just by the need for computational tractability, as where we've got to keep things simple so that we can solve the equations and so that we can derive conclusions from the description of the model. But there are also some, as well, less merely pragmatic reasons for having simplifications in models, at least in some cases. So one example of that is they may also help us to understand better two factors which in practice always occur together by separating their effects. And so an example of that I've been interested in my own research has to do with the role of perceptual limitations as contrasted with computational limitations. So when we're getting knowledge of the external world, there are various limitations on our knowledge coming from the fact that our perceptual faculties are not perfectly discriminating, that in some way they can't pick up reliably all the differences in what's being perceived. But there are also always computational limitations for human beings, because we're not logically perfect, and so you can't have cases where there are perceptual limitations and just no computational limitations at all. There are some computational limitations always there, but in a model, you may be able to basically exclude the computational limitations by just by the way that you structure the model, as whether it's a model of someone who's a perfect logician, but even a perfect logician may have very bad eyesight. I mean, a perfect logician may still have to wear glasses, and then, or you can talk about what they're like when they don't have their glasses, and so on, and so the model building methodology enables us to separate these two factors and study them independently in a way that wouldn't be possible if we were dealing with real life cases. I think another aspect of the model building methodology, which philosophers are often a bit uneasy with, is that the proper use of models is a skill which requires experience of the method and good judgment of the case at hand, and it can't be achieved just by mechanically applying a formula. So this partly involves skill, for example, in choosing an appropriate model, and for example, it may be in judging what's a kind of cheating with model building by just putting in some kind of ad hoc little complication into the model just to give you the result that you want. And that, whereas you're doing something which is too close just to writing in by hand the kind of prediction that you wanted to make. And I think it's very hard to write precise rules for excluding this kind of thing. But philosophers are kind of uneasy where they don't feel that they're being given a completely explicit and precise justification for drawing one conclusion rather than another. And I mean, I think in a way this feature of methodology, it goes beyond just the model building case, but I think it's quite prominent in the model building case that in any science that there is a kind of role for skill and experience which can't be completely eliminated, and it's those factors are certainly there in all over the place in natural and social science. And although some philosophers, as it were, have a very purist idea where they would like to eliminate all of that and make everything just completely explicit and open and mechanical. I don't think that's a realistic ideal for them to be aiming at, and its limitations do become very clear in the case of the model building methodology. So as I say, this kind of uneasiness that you get with analytic philosophers about this aspect of the method, because I mean, they feel that it lacks rigor, and I think it's understandable why some of that unease is felt, and it's not that it's, as it were, dishonorable or anything, but that these are just the some of the sacrifices that sometimes have to be made. And in the model building case, of course, there is one aspect of it which is extremely rigorous, which is that when we're talking about the features of the model themselves, that those can be rigorously derived by purely mathematical means. It's just that there may be a bit less rigor when we're talking about the relation between the model and what it's supposed to be a model of in the other cases. But I think that avoiding a model building methodology, it's not that it enables you to be perfectly rigorous. It just means that the lapses from rigor occur in a different place. And I think the experience of the natural sciences strongly suggests that that by making kind of sacrifices that are involved in the model building methodology, that in the end it can pay off very well. And so, as I say, that what is going on with the model building methodology, that it's just what real science is like, and I think we should not be shocked that this is something that we have to accept in philosophy as well. So, as I've been trying to show, model building has already made a significant contribution to philosophy in some of the areas that I mentioned, like formal epistemology and formal methods in moral and political philosophy, and so on. But I think it's also the case that that lack of understanding and even awareness of the method has almost certainly led to neglected opportunities for its use. And even in philosophy of science, I think that it's taken quite a long time for model building to be fully recognized for what it is. So that, you know, until relatively recently, there was a tendency to try to assimilate all science to model building or something like that. And I think the effect of talking about models in that way was just to dilute the term in such a way as to make it almost useless. Whereas I think that by having a more specific understanding of what models are, it makes it a much more helpful analytical instrument. But the point I want to make here is that that because philosophers have not been thinking in terms of model building, only a few of them have actually been trying to build models. And what I want to suggest is that there's likely to be lots of low-hanging fruit around. In other words, there are likely to be rewards which can be gained from application of the model building methodology relatively easily because it hasn't been applied very widely. so that although it's in effect possible to follow a model building methodology without being aware of it, I think once we're aware of it as a technique that's at our disposal, I think much more of that will happen than before. But as it were, by getting in early, you have the opportunity to get the rewards where there have been maybe topics that have been crying out for the application of a model building methodology, but where that hasn't been done because philosophers are not trained to think of what they're doing in such terms. So what I've been suggesting is that model building is likely to be a growth area for philosophy in the future. Just to emphasize again, I'm not suggesting that model building should become the exclusive, the only methodology for philosophy. I think that would be completely inappropriate, but it is something that deserves to be one of the methods that we use, much more than is currently the case. And so I think we can expect those kind of opportunities to be taken in the future. So in lecture 10, which will be the last lecture in the series, I'm going to be speculating much more widely about future trends in philosophy and to some extent about how they're related to trends in the world outside philosophy. Thank you very much.
Professor Williamson, thanks a lot for your very nice and encouraging lecture on a topic, that's very close to my heart as a philosophical logician who is perhaps picking those low-hanging fruits, as you describe it. Okay, so let me start with some remarks about your lecture. First of all, I really like how you started your lecture with the conception of progress in philosophy, because I think it's really much needed to be discussed. Ideally, human knowledge can be a pile of books like this. It's kind of a monotonic way to grow the knowledge, and when you sort of climb the ladder of books, you'll see more and you can see the beauty of the real world. But in reality, especially for the field of philosophy, I think the situation is like this. You have a rather messy bookstore, and for many students, I think, especially when they're doing their PhD, I think they're sort of trying to find their way in this huge pile of books, not organized in a very nice way. So I think in many cases, they may find lost and need some direction. Okay, and especially as this kind of diagram shows that when you learn more, you actually get into a specific topic, but the thing is you know less and less. Especially for philosophers, you can actually go down below nothing here. So I think it's really important to have a conception of progress, especially in philosophy. And what is worse, so I'm here quoting Hindika. So he said he once read about some story about a cannibal tribe, where if you want to be a new chief, you need to kill and eat the old one. And he thinks some philosophers are dissidents of that tribe. And in the sense that when some philosophers develop a new theory, it's almost important to sort of kill the old theory in a kind of a role of revolutionary fashion. Okay. But from your lecture, I think we see model building is a good way to understand the progress in philosophy. Especially, I think it describes a more constructive progress. I mean, you can build models and others can also contribute and make changes or build a better model. You don't need to always restart from the scratch. And although it's not always monotonic, I mean, you may find some basic assumptions are not so good. You can start a new model, but it's more constructive than the usual practice, I think. And it's also more realistic, as you described. We are not always looking for the universal laws, but with some simplifications and some idealization, we can build reasonable models to make some points. And it's more robust to, say, non-essential counterexamples, I think. And we can test the models with future philosophical evidence or other, say, facts and knowledge. And as you also showed that we can make hypothetical cases more, say, understandable by exploring them in a more rigorous way, I think, by building a model. And also in this way, many people can contribute to philosophy. Because I think currently there is sort of a 0-1 law in philosophy. The greatest philosophers did almost everything, but many people just did nothing in philosophy. It has a very sharp contrast to, say, natural sciences, where a lot of PhD students can also contribute to the state-of-art sort of research. So I think by trying to build models, many people can do something to, say, incremental contributions to model building. Nevertheless, I have also some questions. Actually, those questions, some of them are sort of on behalf of the general audience, because I think many people may have shared the same questions as I do. So first, maybe a basic question is how to evaluate philosophical models. In keeping the, say, analogy with natural sciences and their models, for example, in natural science, you use model to predict things, not just explain the current observations, but also predict things. And with future evidence and future facts, you can sort of evaluate whether the model is good or bad, and you can keep having more and more evidence. But in philosophy, it seems not that usual that you get a lot of, say, new evidence year after year. So I want to know more about your idea on how to evaluate philosophical models. And in your lecture, I think the most examples you mentioned, and also the toy examples, are sort of formal or logical or kind of mathematical or technical. But a question is, in philosophy, if we want to build models, do we always need to build formal models, or there can be informal models which can also make sense and tell you important things about philosophy? So that's my second question. And somehow related to this, I'm also wondering, I think many people may share my question. In philosophy, traditionally we have a lot of theories, but can those theories also be viewed as models? For example, in your lecture, I think most models are sort of semantic in the nature, as you described. But if you think carefully in natural sciences, if you write down those differential equations, they can be viewed purely syntactically, right? It's like in logic, you just write down a few principles, like a logical axioms or just logical formulas. But if you just write down a few principles, it's more like the traditional theory in philosophy, right? So I want to see the more, say, clear boundary between a theory and a model, or can a theory be also considered as a model in certain cases? Okay. And I think also, because you mentioned a lot about the scientific methods and the analogy with methodology of philosophy. So I think a natural question related to this is about this current sort of new trend of doing experimental philosophy, which also, say, use a lot of natural science, methods like questionnaires and doing experiments. And it also draws attention on human reactions, right? So, yeah, I would like to hear a bit more about the connection with experimental philosophy. Okay, next. Because I mentioned this Hindicast quote of killing the old chief. So I guess also in your point of view, model building is not the only or the new way of doing philosophy. So I want to hear your, thoughts about the relation between this model building method and also more traditional philosophical methods. So what are the features and how we distribute the work? So what kind of problem is good for model building? What kind of problem is good for what other methods? Okay.
Okay, thank you. It's my pleasure to be the questioner of Williamson's lecture about modeling of philosophy. And this lecture is very interesting and inspiring. And my question is only one: how to evaluate a model of philosophy? And actually, it is a set of questions, but I want to put them into a title. In what sense a model is better? From page 10 of Professor Williamson's slide of lecture 9, we learned that a model is a simplified description of a case of the phenomenon. And from page 15, we learned that one model can be a better model than another of a given phenomenon by being a closer approximation to actual cases of the phenomenon. And from page 67, we learned that what displaces a model is not a counterexample, but a better model. So my impression is for Professor Timothy Williamson, the more complicated a model is, the better it is. And a further doubt is model evaluation contextual? And I have an example of Chinese diagram of Taiji. And in Taiji, I think there is an aesthetic encouragement of model building or model evaluation. In ancient Chinese philosophy, we have a very beautiful Taiji diagram of this work, and many Chinese believe it is very simple and the best philosophy model of the world. And from page 15, we learned that the same sentence, in the previous slide. So in this sense, progress in modeling is Popperian approximation. But from Doing Philosophy, another famous book of Professor Williamson, he has rejected the methodology of Karl Popper. We learned that model building contrasts with the methodology of conjecture and refutations championed by the philosopher of science Karl Popper. So a question arises, is in the approximation sense, Timothy Williamson is a Popperian. So this is the second doubt. And from page 22, we learned that it will help us understand the origins of vagueness in thought and language. So in my mind, verse, point, song can help us to understand too. So my question is, comparing with other models or other kinds of way of understanding, in what sense a model is better? So this is my question. This is a question of model evaluation. Thank you.
Thank you very much to both of you. I mean, I think those are questions that will probably be worrying some listeners and so on. So I'll do my best to answer, starting with Yan Jing's questions. So on how we evaluate philosophical models, I mean, I mentioned some aspects of this in the talk, but maybe I can add a few other points. So one thing that I've been thinking about recently is about how to make models more model building methodology robust, in the sense that if we have a model that that predicts, let's say, the possibility of a certain phenomenon or something like that, but then very, very slight variations on the model will no longer give that prediction, as where if just slightly perturbing the model was enough to make the prediction go away, then that seems a sort of rather dubious use of model building, and so I think that sometimes what we may need to do is to argue that not just by looking at individual models, but by, as we're putting constraints on models, and then showing that any model that satisfies these constraints will have certain features that we want. So I mean, for example, I'm interested in the using the model building methodology to attack the principle that whenever one knows that one knows, and the KK principle, and I think one can show that results where any model satisfying certain basic constraints will involve violations of the KK principle, and I think that's certainly a more satisfactory method of argument than just producing individual models and arguing that these are kind of realistic and that they involve a violation of the principle. And I mean, I think in terms of the predictions. Of course, it's true that it's not that in philosophy we're getting, as it were, a kind of stream of new evidence that we can use to test models on. But the kind of prediction that one can sometimes make from a model is that, as it were, just by, on formal grounds, one can predict that a certain phenomenon will be possible, and then if you can, as it were, describe a realistic case where this will hold, then that's some support for the model. But it is difficult to give a very sort of I don't think we've got a kind of checklist of criteria and so on. And I mean, of course, it's easier where we're dealing with models which are making quantitative predictions where we can then measure. But as I mentioned in the example of three-sex reproduction, that often we're not doing a straightforward prediction, even in this scientific case, and yet some of those models will be better than others. And I think the various kinds of criteria that I've been mentioning, are relevant, and maybe some more will come out as I answer the other questions. So your second question was about whether models have to be formal, and I suggested that the Wittgenstein language games might be seen as models, and then they're not very formal. But I think there is some point to the formality, which is that one of the big values of models is that we can use them to explore. We can explore the model in a way which it doesn't raise the same epistemological questions as exploring the real world phenomenon. So that what we can do is we can get a whole lot of independent knowledge of how the model behaves, where we don't need to throw in lots of extra assumptions which might be connected to the very things that we're trying to test. We can just look at the model and then and derive the behavior of the model, and it should be that as it were, everyone who's mathematically competent can agree that the model does behave in this way, and the fact that we've got something there that's independent of the very things that we're arguing about is part of the value of the models, and so that would makes them not just sort of completely question-baiting things, and I think that the formality of the models is something which gives them that kind of independence, so that we can all agree at least on how the model itself behaves, and so if we were just describing models in kind of much vaguer terms, it would simply be less clear, particularly with models of any complexity, what features they had. So I think the formality, it's not just being pursued for its own sake or because of some kind of obsession with rigor, but I think it does have this kind of independence which allows models to give us to be some kind of check on us, that they can't we can't just say what we like about them. There's a kind of reality check in the behavior of the model itself. So that's actually related to your third question, which was, can a theory be viewed as a model? And so I think with many philosophical theories, they fail this formality constraint, so that it just isn't very clear what actually follows from the theory, and so you can't simply, as it were, explore the theory to see what holds in the theory, and for that to be kind of an independent check, because the theory is too vaguely formulated for that. Of course, in some cases, we may have a theory which is sufficiently precisely formulated and sufficiently powerful in its claims that we really can just logically or mathematically derive from the theory a whole lot of consequences, and it can at least be agreed by everyone that those are consequences of the theory. And then the theory is to some extent being viewed as a model, but if it's a theory that's been put forward as simply as true, then of course it's vulnerable to counterexamples in the way that models are not vulnerable to counterexamples. And you know, when one looks at the way in which philosophical theories often have been proposed in the past, they have very often been proposed as things which were could be proved to be correct, you know, which were necessarily true, and so on. And where the case for the theory was one which, if it worked at all, would show that it was exceptionless and universally true rather than just a model. Your fourth question was about experimental philosophy, because experimental philosophy is, of course, is another way in which philosophy can resemble a science. So the trouble is, I think, that experimental philosophy is a scientific approach to psychological questions, or perhaps one could say sociological questions about what people believe, basically, or what they're inclined to believe if you ask them a question that they've never thought about. And so, you know, if we took an experimental philosophy, the analog of such an approach to biology, it would be going around asking hundreds of ordinary people, you know, what they believed about biology, whether they believed in the theory of evolution. And of course, the results of such a survey would be interesting, but they wouldn't cast much light on whether the biological theories were in fact correct. And, you know, in the same way, the trouble with X-Phi as a methodology is that it's not really scientifically addressing the questions that we're actually interested in philosophy. It's kind of making philosophy a science by just psychologizing it and making it in effect into a branch of cognitive psychology, if it's treated as, you know, a central method for philosophy. Whereas I think the advantage that the model building methodology has is that it does not change the questions. I mean, that the model building really is, you know, building of models of the phenomena that we're actually interested in, rather than models of what ordinary people think about those things. And so I think, as we're given what questions we're interested in, I think the model building is the scientific approach, much more than X-Phi, which only has this rather indirect relation. Then your fifth question was about the relation between model building and other ways of doing philosophy. And so, I mean, I think it's, I mean, there are, you know, there are many areas of philosophy where it's just very hard to think of a model that would actually contribute. And so, you know, I mean, when one's reading, you know, Kant or someone, it doesn't, you know, it doesn't typically feel as though really what we need here is a model. But of course, I'm a bit, you know, I want to be cautious about this because the model building methodology has not been tried very much, and you know, and it may be that it's actually has much more capacity, you know, in unexpected ways than there might have been thought. And you know, and in the case of epistemology, I think the kind of contributions that epistemic logic has made have been, you know, many of them have been in areas where it didn't particularly seem in advance that model building could help, but in fact I think it has helped. So I think really what we should be doing is, as it were, attempting all over the place to use models, and then it may be that we will learn from that there are certain areas which are genuinely really recalcitrant to model building, but I think it will be difficult to confidently say that until we've tried harder than we've tried so far. And I certainly don't think that we should be giving up other methods at the same time anyway. In the same way that if you take the whole field of natural science, I think it might be quite difficult to put your finger on any bit of natural science where model building was in principle irrelevant, and it might turn out that philosophy is like that. So those are very brief and rather schematic, sketchy answers to Yanqing's questions. So now I'll say something about the questions that Wei Ping was asking, which of course to some extent overlap with Yanqing's questions. So Wei Ping was wondering at one point whether I thought that the more complicated a model is, the better it is. And I certainly do not think that, because you can, I mean, if you take any model, you can easily build in lots of silly complications to it with, which would just make it worse. I mean, my view, in fact, is that it is better to keep models as simple as they can be, in part because what we want to use models to explore the phenomena, not just to give us the answers that we, as it were, for independent reasons wanted to hear. And and if we allow ourselves to get too complicated with models, it becomes, the more complications we allow, the easier it is to make the model just say what we want it to say, and as where the model becomes our kind of puppet. Whereas it's better, to have a model which is fairly simple, and then we just define it by a few key stipulations, and then we can let the model run and see what it does, and it may tell us something unexpected. And so I think by kind of insisting on that sort of simplicity, we we may learn more. And I think that's also related to an issue that Wei-Ping raised about aesthetic encroachment, about, as it were, still about the role of aesthetic standards. And in general in philosophy, I tend to think that aesthetic criteria actually have a very positive role to play in cognition, even though it's quite difficult to explain why. But maybe I can just, this is not by any means a full answer to the question, but just give a kind of hint. So if we think about why we find symmetry attractive, I mean, we find it attractive in in architecture and all sorts of things. My guess is that the evolutionary explanation for the attraction of symmetry is, or at least part of it, is that asymmetry, lack of symmetry in another member of your species is usually an indication of ill health or disease or something. Because talking about animals that have some kind of natural symmetry as human beings do, so that if they're asymmetric, something's probably gone wrong on one side or the other, and so symmetry is kind of serving as a sort of an indicator of health, even though of course health and symmetry are not the same thing. And I kind of feel that in a model, an aesthetic criterion such as symmetry is sort of acting as an indicator of the health of the model in some sense. Of course, that's quite metaphorical, and it would, to make anything proper, one would have to develop that thought much more. But as well, that's a kind of picture of what might be going on. Then I was fascinated by what Wei-Ping was saying about the Taiji diagram, and it would be, of course, I don't know to what extent the people who produced, I don't know anything much about it, but whether they were thinking of it as in a kind of model-like way, or as just fundamentally how things actually were. But maybe they were thinking of it as a model, and so it would be very interesting to know more about that kind of early model building approach, if it can be thought of in that way. And then when you were asking whether model evaluation was contextual, I think it could be contextual in a number of different ways. Of course, what is mathematically the same model, it obviously can be a good model of one phenomenon and a bad model of another, so that what we're trying to model makes a difference. And of course, it also makes a difference when at what time it's being evaluated. Something that a model that was an important contribution at the time that it was first advanced, would not, it's 50 years later, it's not the state of the art, and so we have a lower evaluation of it, at least comparatively. Then you were asking about my relation to Popper, where I was making some very critical remarks about his sort of falsificationist method of conjectures and refutations. And and then you were mentioning that there's maybe something Popperian about the idea of better and better models being better, in some sense, approximations to the truth, which that's reminiscent of Popper's sort of later idea of verisimilitude, of that scientific theories may approximate better and better to the truth. And actually, verisimilitude, as it happens, was what I did and approximation to the truth was what I did my doctorate on many years ago. So I think one problem with Popper's work is that I think he wanted the method of conjectures and refutations to be somehow fully consistent with the idea of verisimilitude, and that the purpose of theories was increasing verisimilitude. But there isn't any very clear connection between the two, and it's certainly not the case that by rejecting one theory because it's been falsified and then going for another theory that's consistent with the evidence so far. That certainly might involve a loss of approximation as well to the truth, as well as instead of a gain. And so I think there are these different ideas in Popper, some of which I'm more sympathetic to than others, and I don't think that that he fully reconciled them. And in fact, when he's talking about the increasing verisimilitude, he sometimes somewhere says that there's a whiff of inductivism, which of course inductivism is exactly what he's trying to avoid here. But it seems that he's kind of somewhat aware that there is a tension, but because it's particularly on his own, given his own epistemology, it's very hard to see how he's entitled to make the claim that the method of conjectures and refutations is also a way of increasing verisimilitude. But and so I'm siding with roughly speaking, with one aspect of Popper against another aspect of Popper. And then one last thing in answer to some of the questions that you were asking towards the end about, what's so good about models, is that I think one great advantage that models have. Oh yes, you were comparing them to songs and poems and things that may also inspire us. It's true that a song or a poem may inspire a particular insight, but one thing that a model has is that a model is something that can be explored as a kind of proxy for the phenomenon that we're concerned with, so that we can fiddle about with a model. We can ask what will the model, or it's in fact a class of models of the same type or something like that we're exploring. What will happen if we change this little bit of the model? What will the effects of that be? And so it gives us something that we can explore in a scientific way that is somehow acting as a kind of proxy for the phenomenon. And I don't see that poems and songs and such things can quite serve that purpose. I mean, of course, they can. I mean, it's true that they can inspire more than one insight, but I don't think that they can be explored in that very free way that that a model can be. And you know, a model is something that you can play with, but that also has a very robust reality of its own. So you can ask it lots of questions, but then the model, as it were, will give you an answer, and you can't really argue that that is the answer that the model is giving. It's just a mathematical fact that it's giving you that answer. Whereas, you know, with a poem or a song, I think because it doesn't have that kind of formal aspect, which we can't just interpret however we like. You know, it's much easier to convince yourself that a poem is telling you is giving you the answer that you wanted to hear, whereas the poem, you know, it's endorsing the choice of action that you want to take. Whereas with a model, you can't just do that in the same way. It's kind of you know, it resists wishful thinking and reinterpretation, you know, to a much higher degree, and I think that often makes it a better reality check than a work of art, despite all the great things to be said about works of art. Okay, I think I've been talking for enough, and although, you know, a lot of the questions that I was being asked, they certainly deserve more discussion, but I mean, there are at least some hints about how to answer them. So thanks.